How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business, and more especially now the physics of toys. And as you might guess, it is filled with enchantment for me. So, our first program, already done, I devoted to the physics of mechanical toys. Mechanical. Let me now explore a little with you some toys that have acoustic mechanism and thermal mechanism. Acoustic. Let me go back to one I did before. I talked about the mechanical properties of a toy gun, where we can determine the range, the maximum range, and such other properties of projectiles. I did not explore the acoustic properties of this. Now, what have I done? I have lodged this ping-pong ball in this chamber, compressing some air in there. Now I'm going to shoot the ball. And there is an acoustic property that is not so easy to understand. Listen, listen. Up, poop. And I want to know, thank you, sir, I want to do it again. There it is. And I want to know where that sound came from. And that is very difficult. And because it is, I will abandon it here and now. But this all suggests what? That the physics of toys is not trivial. Consider another one. Here is a disc with some holes in it. Some holes. That's good. And the other side is a disc with some holes. So there are two discs, like pie plates, put face to face. And here is a string, and there is a string, and you are, of course, reminded of the toy of the button on the string, the pair of strings. Now I am storing some elastic energy in the wound-up strings. Wound up. And now, listen. And I want to know where the sound comes from. But more important, watch the string. Watch the string now. Watch it. Watch it. Do you see? I'm going to do it again. Let me show you what was going on the string. Very wonderful thing. Here is the disc here with the holes. And there is a string, and there is a string. And here's what we saw. Here's what we saw. A standing wave on the string. And the standing wave is the behavior of a vibrating string, which is resonant to the pitch of the note emitted by this spinning top, or whatever you want to call it. Now, I'm running out of steam there a little bit. So, consider another one of the same equivalent substance. This is two hemispheres put together with holes in them. But you will see they have a different pitch, a different frequency. And again, standing waves on the strings. Now, consider something much more difficult. Here is a little airplane with a string fixed to the nose, and here is a little stick, and the string, which is a piece of nylon string, is fixed around this shaft here. Now, I'm going to hold the string tight and turn the shaft, and you listen. Listen. Now I'm going to do as a child would do with the toy. And I will suggest the mechanism. The string on this little shaft, like the rope, the hawser with which a ship is tied to a bollard at the dock. That's what that looks like, a bollard, rope tied around it. What happens when I turn this? The string grabs and lets go. Grabs and lets go, which means that the nose of the plane is pulled so and pulled so and pulled so, quite like a violin bow grabbing the string and letting go, which is how a bow activates a string. Now, here is another such toy, which is in the shape of a bee, And this one has an empty chamber, a little chamber, empty, correction, filled with air. Now, I view this chamber here as an open pipe of certain length, and it has a certain pitch. Certain pitch. Now I'm going to close that pipe with a stopper. It is now a closed pipe of certain length, and it will certainly have a different pitch. Right. And so we could make a comparison between open pipes and closed pipes, say, in an organ arrangement. Or, I'm still on acoustic toys. My little bird whistle. Here is a little chamber in which is lodged a piston. Now, the chamber is that long, and the piston could be pulled out the entire length of the chamber. I wanted to discover what change takes place in the pitch of a note when the chamber is heated. Because, as you know, when orchestras play, and the musicians get hot, and the hall gets hot, and the conductor gets hot, and the instruments get hot, and the people breathing get hot, and the whole place is hot, some things happen to the strings and to the winds. The strings get less in tension, and their pitch goes down, but the wind instruments have their pitch go up. I wanted to explore that, so what did I do? I am blowing this whistle, holding a lighted candle here, and I nearly ruined my whistle, as you can see. But anyway, for the length that I have available, listen to the change in pitch. Change in pitch with change in length of air column. Marvelous thing, marvelous.